Hello. So in this lecture we are going to talk about the Laplace transformation of unit impulse functions and of periodic functions. Okay. So first regarding the definition of a unit impulse function. So unit impulse function is also known by the name direct delta function, and by impulse we mean force acting for a very short duration. Okay. So let a be greater than equal to 0, and the unit impulse function or the direct delta function is then defined as the limiting case of this force which is acting for a very short duration, and we denote it by delta epsilon t minus a, where epsilon is the duration at the say time t is equal to a. Okay. So the force which is acting for a very small duration epsilon at a, so for t a to a plus epsilon the force is 1 by epsilon, and otherwise this is 0. So there is a force which acts for a very small duration of epsilon at the point a, and this impulse is generated, and otherwise the force is 0. Okay. And we call it a unit impulse because of the property that if we integrate this function from 0 to infinity, then that value is 1. So if you integrate this from 0 to infinity, then then we can divide this integral as 0 to a to a plus epsilon, and a plus epsilon to infinity. So function value is 1 by epsilon only for a to a plus epsilon. So we can write that this integral equals a to a plus epsilon of 1 by epsilon dt, and then we can integrate, substitute upper limit minus lower limit, and we'll see that the integral value is 1. Okay, so this is a unit impulse. And this unit impulse function is actually the limiting case of this. That means this epsilon goes as small as possible, so taking limit epsilon tending to 0. So limit epsilon tending to 0 on this function delta epsilon t minus c, we get the unit impulse function, which we now denote as delta of t minus a. That means the impulse at t is equal to a, and as epsilon goes to 0, so this 1 by epsilon goes to infinity, and as epsilon goes to 0, this duration a less than t less than a plus epsilon becomes t equal to a. Okay. So with the property, this still hold that the integral from 0 to infinity for this force is 1. Okay. So with the property that 0 to infinity delta t minus a dt is 1. So this is a unit impulse. Okay. That at the point a there is a impulse force satisfying this property. Okay. It's just like we saw in cricket, the sneakometer shows the when ball passes the edge of the bat, if it touches the bat, there is the impulse generated. Okay. So now the question is whether we can find the Laplace transformation for this impulse. Okay. So let us see how we can do that. Okay, so the Laplace transformation of the unit impulse function. So let ft be a function of t continuous at t is equal to a, and so if we calculate the integral this, then 0 to infinity ft delta epsilon t minus a dt, if we calculate this integral value, then by definition delta epsilon t minus a, it equals value of 1 by epsilon only in this duration a to a plus epsilon, otherwise this is 0. Okay. So this integral immediately reduces to integral of this, and 1 by epsilon is a constant, goes outside, and because ft is a continuous function, so by mean value theorem of integrals, uh, there exists a c between a and a plus epsilon, such that we can write the integral value as upper limit minus lower limit times function value at c. Okay, for c between these two lower and upper limit, and then epsilon cancels out, and because a cancels out here, and this value is epsilon, and it gives value the f of c. Okay, and if we take limit epsilon tends to 0 on both sides of this, then immediately we get that 0 to infinity ft and delta of t minus a dt is f of a, because as epsilon tends to 0, then c becomes a. Okay, so f of c becomes f of a. So the integral 0 to infinity for a ft function times the unit impulse function, its integral is a function value at a. Okay, so this impulse is at a, so it this integral value becomes the this function value at a. Okay, so if you remember the definition of Laplace so transformation, then we know that Laplace transformation of any function, okay, is 0 to infinity e raised to power minus st of that function dt. Okay, and then if you compare these two integrals, then this ft is e power minus st. Okay, so if this integral is equal to fa, then this integral must be equal to e power minus as, because t convert changes to a. So here if I put let's see, ft is e power minus st, so f of a will be putting t as a, so e raised to power minus of a. That means the Laplace of unit impulse function where impulse is at point t is equal to a is e raised to power minus a. Okay, and if a is 0, then we can have the Laplace of unit impulse function at origin, and it is equal to 1. Okay, because e raised to power 0 is 1. And then so we can easily write the result for the inverse Laplace. Okay, so the Laplace inverse of e raised to power minus as will be delta of t minus a, and Laplace inverse of 1 is delta t. Okay, so these uh, results for the impulse function you can remember. Okay, and say I take one example from the electric circuits. Say example says that an impulsive voltage of E delta t is applied to a circuit consisting of LRC in series with zero initial conditions. If I be the current at any subsequent time t, find the limit of I, that is current, as t tends to 0. Okay, so there is a impulsive voltage at origin applied and is constant here. Okay, so because there is a impulse generated at time 0, uh, so and initial current is 0, even then for a very short time the current value current will be generated. So let us see this. We know that for LRC circuit the differential equation which satisfies this circuit in series is L di by dt plus Ri plus 1 by C integral 0 to t I dt is equal to the voltage E delta t, and given the initial condition that the current initially is 0. So we have a initial value problem, and so we can solve this using Laplace transformation and find out the value of current which satisfies this differential equation. So we know how to solve a differential equation using Laplace transformation. Take Laplace transformation on both sides of this equation, that's first step, and then we will substitute the initial condition. So taking Laplace transformation on both sides of this differential equation, so Laplace of left hand side equals Laplace of right hand side. Okay, so I've given Laplace symbol as bold L, so that to differentiate with this L symbol of inductance. Okay, so by linearity we can solve the left hand side. Laplace of sum is sum of individual Laplace. Okay, so Laplace of first term plus Laplace of second term plus Laplace of third sum equal to Laplace of right hand side. And then we know if we denote Laplace of I current as I of s, okay, then we can immediately have the Laplace of derivative of I, the property, okay, of derivative, and Laplace of integral, because we have know the Laplace of integral of function, the property is there. Okay, so applying Laplace on the derivative, so we have sis minus I0. Okay, that's for first derivative. and Laplace of I is is, and for the integral we know that Laplace of integral of I will be 1 by s of is. Okay, and right hand side Laplace of delta t is 1. So this is step 1, and in step 1 then we substitute the initial condition, so I0 is substituted 0 here. Okay, and then we solve this equation for the unknown is function. Okay, so we collect the terms of is, and then we calculate is from here, so is will be e over this quantity. Okay, right. uh, then third step is take inverse Laplace on both side of this equation to find I current. Okay, so the for the third step, just going back. Okay, for the third step, denominator is a quadratic term, so we try to make a whole square here for so we this is like s square plus 2as. Okay, so we add a plus a square and minus a square here to make a complete the square in the denominator. Okay, so it's like s square plus 2as, so 2 times 2 multiply and divide by 2, so r by 12 will be like a, so we have this a square and then minus a square plus some quantity which is already there. Okay, so this first three term will combine into a whole square of s plus r by 12 whole square. Okay, right. And if I call this as a r by 2l, so it is s plus a whole square, and this quantity I'm calling as b, so it becomes plus b square. Okay, so a is r by 2l and b is this quantity, b square is this quantity 1 by lc minus r by 2l square. Okay, just to write it in a simpler form. Okay, then at last we can substitute back our a and b square value. Now we can apply inverse Laplace transformation on both sides to write this as it, and here we can use first shift. Okay, so Laplace inverse of is it, and e by l is a constant outside, and Laplace inverse of rest of the stuff. And then by linearity, or by first shift, we know Laplace inverse of f of s minus a is e power at, so we can have e power minus at outside. Okay, by Laplace inverse, and so s is substituted as s minus a, so it becomes s minus a over s square plus b square. And by linearity we can separate s over s square plus b square and a over s square plus b square, and so Laplace inverse of s over s square plus b square, we know it is cos of bt, and Laplace inverse of b over s square plus b square is sin bt. So for the second we multiply and divide with b, so a by b times sin bt we can get. Okay, so e raised to power minus 8 is already there, cos bt because of s over s square plus b square, and a over b sin bt because Laplace of sin bt is b over s square plus b square, so b will cancel out and we'll get a over s square plus b square. Okay, so this is the current at any time t in the circuit, and if I take a limit t goes to 0, then exponential will become 1, cos of 0 will be 1, and sin 0 will be 0. So as t time approaches 0, there is a current in the circuit e over l. Okay, so this is a current at in general at any time t, and as t goes to 0, there is a current in the circuit e by l. Even when initially the current is 0, still for a very short time there is a current in the circuit due to this uh, E, okay, which we said is a impulsive voltage. Okay, applied at time 0. Okay, so this is one example on impulse function. The second definition today that we are going to take is finding Laplace transform of periodic functions. So if you are given a periodic function, so first of all we know that a function is said to be periodic if there is a positive number p, which we call the period of the function, such that f of t plus p equals ft for all t in the domain of the function. Okay, so for example, say the function in this graph, okay, it is periodic, okay, because it is the same curve repeating after a fixed interval. And so you can see that the period here is b, okay. So after t is equal to b, the graph is repeating itself, okay. So this function graph is periodic with a period equal to p is equal to b, okay. And for just one period, if we have to write the function, say for this first curve, then we can write it as f1t as a over bt for t0 to b, okay. Okay, because a by b is the height oblique base, so that's the slope of this curve, okay. So and this curve passes through origin, so this first period we can write that it is a over bt, okay. So if we have to calculate the Laplace of this periodic function, then how we can calculate the Laplace of periodic function? By using just one period of that function, okay. So the Laplace of periodic functions, if function ft is periodic with the period p greater than 0, so that this is satisfied, f of t plus p is ft, and f1t is one period of the function written using unit step functions, okay. So if you have a function, then because it's just one piece, so we can use unit step to write that function. And so the Laplace of the periodic function, complete function, is equal to 1 over 1 minus e raised to power minus sp, where p is the period, times Laplace of f1t, where f1t is the function for one period, okay. So Laplace of the complete function can be calculated using the Laplace of one period function for one period, okay. So let us see this the same graph again, okay. So if you are given this graph, then for we said that for one period the function is this, okay. And so we can write this using unit step, okay. We know that this function can be written as a by b times t multiplied with the unit step at 0 minus unit step at b, so u of t minus u of t minus b, okay. So we can easily write f1t as a by b t this times ut, okay, minus a by b t times u of t minus b, okay. So that we have written into two parts here, okay. So if I just multiply this a by b with b, it will be plus a ut minus b, which will be cancelled with this, and we'll get a by b t ut minus b, which is this function multiplied at the upper limit, okay. The other way, as we discussed in previous lectures too, we can write this directly from here, okay. So if I am talking about this curve of one period, then at origin uh, is the first piece with slope a over b, so we have a over b t ut, and then at point b the slope changes from plus 1 to 0, so we get uh, slope of change in slope is minus 1, so we get is minus a by b t b minus b ut minus b, and also at the point there is a jump of minus a unit, so we get is a minus a ut minus b, okay. So you can see previous lectures on how we can write directly from the graph the function in terms of unit step functions, and then we know how to calculate the Laplace of this, okay. So Laplace of f1 will be Laplace of this, and then we can use linearity. The Laplace of sum will be sum of individual Laplace, and then a by b is a constant, and for Laplace of t ut, uh, ut is at origin, so e raised to power 0 is 1, and so Laplace of t is 1 by s square. For t minus b ut minus b, Laplace if we take, then we will get e raised to power minus bs, okay. And then Laplace of t is 1 by s square, and similarly here it will give e raised to power minus bs with Laplace of 1 as 1 by s, okay. So we have the Laplace for a function of one period as this, okay. So here s square we can take outside, and then the Laplace of the complete function ft will be 1 over 1 minus e raised to a minus sp. Here period p is b, Okay, so 1 over 1 minus e raised to power minus sb will be multiplied. So 1 over 1 minus e raised to power minus sb, a over b s square. So a over b s square is taken from denominator and rest of the quantity in the bracket. Okay, so we simply use this result after calculating the Laplace for one period to write the Laplace of the complete periodic function. Okay, say I take one final example. Say find the Laplace transformation of full wave rectification of sine t. Okay, so if you have this curve which is full wave rectification of sine t, then you can see that this curve is periodic with the period of pi. Okay, so 0 to pi, this curve, then it is repeated and repeated and repeated. So okay, it is periodic with the period of pi. Okay, so we can write the function for one period. F1t is sine t, where t varies from 0 to pi. Okay, so function is periodic in t to pi, t is equal to pi, and for one period we can write function as f1t is equal to, this is the curve for sine t. So sine t times unit step function at lower value minus unit step function at upper value. So ut minus u of t minus pi, or we can multiply this to write sine t ut and sine t ut minus pi, and because we have negative sign, we can write minus of sine t as sine of t minus pi. Okay, so now we can take the Laplace on both side and use linearity on right hand side to write that Laplace of sum is sum of individual Laplace, and then Laplace of sine t, we know it is 1 over s square plus 1. Okay, and here it will be e raised to power minus pi s into Laplace of sine t, which is 1 over s square plus 1. Okay, so Laplace of this is 1 over s square plus 1, and Laplace of this second quantity is e raised to power minus pi s over s square plus 1. Okay, and so Laplace of this full wave rectification of sine t is equal to this quantity multiplied with 1 over 1 minus e raised to power minus ps, where p is period and p is pi here. Okay, so Laplace transformation of ft is 1 over 1 minus e raised to power minus pi s, okay, where pi is the period, times this quantity, which on taking LCM we can write this. Okay, so this is how we can calculate the Laplace of periodic functions. Okay, so I just close it here, and now I will start with another lecture series on the topic of Fourier series. Okay, have a very good day.